Good morning. So here we are, chapter 38. We are doing full-blown quantum mechanics. This is it, right? So I always feel like we've been, the way textbooks organize this material, we've actually been doing quantum mechanics for a while now, right? We saw this back when we were looking at light. We had chapters 34 and 35 looking at what were called wave properties of light, but what we found was it was interference effects due to different paths that the individual photons of light could travel. I guess I'll just stay on here for a minute. And so now we're ramping up everything that we did before. So everything we did before in chapters 34 and 35, we were looking at, full-blown quantum mechanics for light. So let's see where this chapter takes us. Here's a list of all the topics that we're going to be looking at. I'm going to introduce each one as we go along. Here's a couple statements that the textbook starts out with. It says that quantum mechanics needs to be able to incorporate this wave-particle duality that they talked about a lot back in chapter 37 and 34 and 35. It needs to be able to explain the quantum states or the quantum energy states in atoms and molecules. So I kind of squeezed this stuff in here, kind of the basic ideas of quantum mechanics. Everything consists of fundamental particles. So there are these fundamental units: electrons, protons, neutrons, neutrinos, photons, that everything's made out of. And all of these particles have what we consider to be wave properties, or even better, think about this as phase. The phase that we're going to be talking about here in this chapter and in previous chapters, it's not quite the same thing as something waving back and forth. It's more of an abstract mathematical property that these particles have. So it really doesn't have a classical analog to it. So anyway, I'm going to start with those two statements, and then we'll see how those develop. Now, early in the chapter, they make this comment. They say that electromagnetic waves, so-called waves, have oscillating electric and magnetic fields. What's oscillating in a matter wave? So they're claiming that oscillating electric and magnetic fields, those are somehow this wave effect that we're talking about, and it's really not the same thing, and we'll take a look and see why not. But we are going to be reintroducing this thing that we call, this mathematical function that we call the wave function with the symbol psi. Now, the textbook didn't use the terminology wave function and psi. We did in chapters 34 and 35. If you remember, each path of the photon, when we had, for example, two slits that created two possible paths for the photon, each one of those paths had a wave function associated with it. And then we could add those wave functions together using the phase diagrams. And then finally we could square those wave functions to find out what the intensity would be for the light at a particular location. So all of those things that we did with the two slits or the multiple slits or the diffraction effects, they apply to everything. It's not just light, it's not just photons. This is going to apply to electrons and protons and neutrons and neutrinos also. All right, so this is a quick aside, and then we'll get back to chapter 38. But I do want to go back. This is a common misconception, and we often reinforce this in our physics textbooks. So anyway, here is a picture from chapter 31, back from Physics 4B. And here is a radio antenna, let's say, for example. So here's an antenna, and radio stations generate their radio signals by oscillating charges back and forth. Now, when a charge is oscillating, it's accelerating. So the key here is not the oscillation part, it's whenever charges are accelerating, they radiate electric and magnetic fields. And so those fields propagate outwards away from any accelerating charge. Now, what this is showing is as the charges within the antenna are oscillating back and forth, at some times they're going to be generating electric fields oriented in the upwards direction, and at other times they are going to be creating electric fields oriented in the opposite direction. Now, it actually turns out, if you were in Physics 4B here at Laney, I guess, in one of my classes, if you were in Physics 4B, what we talked about was when the acceleration is in this direction, the electric field being produced is actually opposite. It's opposite to the direction of the acceleration. And so as the charges oscillate back and forth, and this electric field effect propagates away, the electric field actually has, okay, and I did that wavy thing, which I'm not supposed to do, so let me take that back. So what I'm going to do is, I'm not going to follow the wave, I'm going to follow points along the direction of motion. And that's because what these vector symbols are keeping track of for us, the electric field is not oscillating back and forth, its magnitude is changing from one location to the next. And so there's nothing traveling in that direction. What these different lengths of the vectors are telling us is that the electric field is stronger at that direction, and then it gets a little less and a little less, and right there the electric field goes to zero. And here it's not very large, but it's in the opposite direction, and so you can see that there is nothing following a wavy trajectory here. Things are just going forward. And this shape that we draw when we talk about radio waves, for example, is this variation in the strength of the electric field as we move forward away from the antenna. All right, so the shape here, this oscillating shape, is a result of the oscillating acceleration of the charges. So that's why it looks like that. If we had a different situation, let's say instead of accelerating the charges back and forth, what if the charges were somehow able to continue accelerating in one direction? Well, if the charges in the antenna were only accelerating in one direction, then the electric field propagating away would only have one orientation to it. So you don't have to have this pattern here of the acceleration. So here's the picture. Here's Physics 4A, a quick review. So here's a charge oscillating back and forth. And as a result, we're getting these variations in the electric and the magnetic fields. We've been specifically talking about the electric fields, but the magnetic fields around accelerating charge form loops, and the direction of the magnetic field within those loops reverses every time the acceleration reverses. So the magnetic fields also are following that. Now, if we were to take an individual charge and watch it oscillate back and forth with some amplitude, which we've labeled here as plus A and minus A, we could write down equations for the charge. X, position as a function of time, velocity, acceleration. If we decide to use a sine function to represent a charge oscillating back and forth in our antenna, then the velocity would follow a cosine, and the acceleration would follow opposite the sine. So it would be a negative sign. And the formula, which textbooks usually fail to introduce, that's the electric field generated by an accelerating charge. So anytime we have a charge accelerating, we're going to have something that looks like that. KQ over R, A over C squared times sine theta. Now, if we take this acceleration of this oscillating charge, the oscillating electron, and plug it in for the acceleration, then we get electric and magnetic fields that are propagating away from the charge, and the strength of those electric and magnetic fields, they match each other. The strength of the electric field is exactly the same as the strength of the magnetic field once we put in an extra factor of C to make the units match up. I'm not sure what this is doing off by itself. KQ over R, omega squared A over C squared, it's the very same strength. So these are the propagating electric and magnetic fields that you guys saw in chapter 31. And again, they are oscillating in a fashion that matches the acceleration. Again, as we were saying, if instead of having the charges oscillate back and forth, what would happen if we were somehow able to just have the charges continue accelerating? Well, then we wouldn't have that wavy shape for the electric field. The electric field would just propagate away, and the direction of the electric field would stay fixed. The magnitude of the electric field would keep coming off of that antenna at a fixed value. And the waviness would be gone. Now, there would still be what we call phase. So the individual photons that make up this electric field would still have a phase property that varies with location and with time. So again, that's what it would look like if the acceleration were fixed. This was the picture that at least I drew back in Physics 4B, talking about this accelerating charge effect. If I have a charge and it's accelerating in some direction, it's going to radiate electric and magnetic fields that are proportional to the, that's an A, that's an acceleration right there, A over C squared. And it's going to spread out away at a speed of, well, at the speed of light. So R is equal to CT. The electric and magnetic field propagates away from the charge. And the way that the electric field is oriented, it kind of wraps around the charge. If you can see these electric fields pointing back away from the direction of acceleration. And the magnetic fields are looping, and they're looping in a right-handed fashion. So this was all Physics 4B. You guys don't have to remember any of this. It's just one of those misconceptions that comes up in textbooks. I want to get that cleared up because it's so important. It's such an important part of physics and engineering. In fact, I threw in one of my examples from Physics 4B here. Here is KQED, FM radio. I know you guys listen to KQED all the time. The power of their antenna, 110,000 watts. I converted that into EV. It works out to be 6.88 10 to the 23rd EV per second. So that's like a mole of photons coming off their antennas every second. Or I'm sorry, EV. So it's more than that for the photons. That's the number of EV coming off. Now, KQED is 88.5 megahertz. So from that, we can calculate a wavelength as C over F. Now, the wavelengths for their electric, and here it is oscillating charges. The electric and magnetic fields do have that variation as you look along the path they're traveling. The wavelength is 3.39 meters. The energy of individual photons is 366 nano eV. So I'm using our 1240 that we started working from back in chapter 37 to find out how much energy. Now, this is radio portion of the spectrum. So, visible light has like photon for photon. That's like 1 billion times more energy in a visible photon compared with a radio photon. So instead of having EV, we've got nano EV. I guess it's not 1 billion, it's more like 10 million times as much energy. Something like that, 10 million times more. The photon rate. So if we take that total power, the 110,000 watts, and convert into EVs per second, and then each photon is 366 nano EVs per photon. It says we got like 2 times 10 to the 30th photons coming off that antenna every second. Okay, so you can see it's an enormous, enormous number of photons coming off, and you need that if your listener is going to have enough photons to get enough resolution to actually listen to your program if they're traveling a good distance away from your antenna. Okay, an enormous number of photons. All right, let's get back to chapter 38. So here we are back with the wave function and its interpretation. Now we did this with light, but now we're going to be able to do this with electrons. So rather than doing this with photons, we can do this with electrons. There was a variable intensity on the screen, and it had to do with following the paths that the light was traveling, or the electrons in this case, we're going to be using electrons, and coming up with constructive or destructive interference patterns. So electrons are going to behave the very same way. We can create two-slit interference patterns, for example. All right. So here is this idea of wave functions, and now the textbook is on board with us. They're using the same idea. Wave functions are talking about how to represent these particles as they follow along some particular path, as they go from point A to point B. Now, all the information of a particle is contained within the wave function. We just have to set it up the right way so that it has the right properties to it. It turns out that, we talked about, again, I guess it was just chapter 37, momentum is related to wave number, or wave number is related to momentum, and that the frequency is related to energy. So energy and momentum are going to determine the phase properties of these particles. And for a free particle, a particle that's just traveling out on its own, a free particle going from point A to point B, nothing's getting in its way, it's not bumping into anything, the wave function for those, the kind of generic starting place is to define that as some kind of a normalization constant, some kind of a constant out front, times e to the ikx times e to the minus I omega t. Now, we saw that we could use, we saw that the book tends to use sines and cosines, but it turns out sines and cosines aren't the ideal functions to be using for these wave functions, and let's take a look and see why. With this definition of energy and momentum, what we can do is we can define what's called an energy operator, and we can define what's called a momentum operator. We can take the wave functions and we can run a mathematical operator on the wave functions in order to find out the properties of the particle, and this is how it works. So if I took this energy operator, which, see, I made it like a fancy E letter, and then I defined it, that's what the three lines mean. I'm going to define it as I times h bar, Planck's constant over 2 pi, and then multiply by partial derivative with respect to time. Now we'll see in a minute why that operator works, but let me just say this much right now. When we come back and look at the wave function, see how in the wave function using these exponentials, see how I can factor out the x dependence and the time dependence. So if I'm taking a partial derivative with respect to time, it's only going to affect the time dependent factor. It's going to bring down a factor of minus I omega. I hope you guys are already imagining taking derivatives here. For the momentum operator, well, the momentum part of the wave function is right there. See where it says e to the ikx? Well, k gives us information about the particle's momentum. And so I'm going to define the momentum operator as minus IH bar partial with respect to x, and let's see how those operators work. So here we said is our general, generic, plain vanilla wave function, which is just propagating from one location to another. So here is the generic wave function. If I take my energy operator and I carry out the series of operations that it defines, now it was defined as I times h bar times partial with respect to t. What that really means is we start at the right side and work our way through the operator. So we would first of all take a derivative with respect to t, and then whatever we get, we would continue to operate on that wave function by multiplying by I h bar. So this is going to be done in two steps. First of all, we take the time derivative, and then we take a factor of I h bar and multiply the result. So let's try that. I'm going to take that wave function, I'm going to plug that into the operator. Now when I take a time derivative, we mentioned this, the only thing that's going to be affected is the time-dependent portion, and that's going to bring down a factor of minus I omega. So now what I have is I've got the whole wave function back again, but I have an additional factor of minus I omega. Now, you guys, I'm hoping you guys have seen complex numbers. You're supposed to have in your math classes. So I is the square root of -1, and if I take I and multiply it by I get -1. And then if I have an additional minus sign, that's just going to become 1. So I times -I is 1. And that means that the i's go away, and we're left with h bar times omega. So operating on this wave function gives me back h bar omega times the wave function. Now, this tells us that the wave function itself is what we call an energy eigenstate, or an energy quantum state. So this particular wave function corresponds to a very definite amount of energy. And that amount of energy is given by h bar times omega. So by plugging the energy in here, when we take the energy operator, we get the energy back, and you're thinking, wait, this sounds kind of circular. It's not so much, well, everything we do, in some sense, is kind of a circular argument, right? We're just looking for consistency, we're looking for mathematical consistency, and we're looking for something that correctly predicts our observations. So if you remember, we had written down these equations showing how frequency and wave number are related to momentum and energy, and that's what we've done, is incorporate that into the mathematics. So, so yeah, we have a mathematically consistent definition for an energy operator. We can do the same thing with the momentum operator. You can try that yourself. I don't think I'm going to step through that, and I might quickly. But these energy and momentum operators, what they're going to do is give us back, the energy operator will give us the energy times the wave function again. Now that should look kind of like linear algebra. So what we're doing is we're solving eigenvalue equations in linear algebra is kind of what's going on here. Momentum operator, we said, was taking partials with respect to x. What that's going to do is bring down a factor of ix. Now, we define this factor out front to have a minus sign. It's minus times ih bar, and that's because when we take the partial with respect to x, we don't bring down a minus sign. So we need a minus sign out front here so that the I and the minus I multiplied together become 1. And then here we have h bar times k, and that's the same thing as momentum. So again, this is a mathematically consistent way that we've gone in and defined what wave functions might look like and what energy and momentum operators might look like. Now, going back, I guess so going back to here, what would have happened if, instead of using complex exponentials, what if we had used sines and cosines? And the sines and cosines wouldn't have worked. If we had done a derivative with respect to using a sine or cosine, we would not get the same function back again. Exponentials have that important property that when we take a derivative of an exponential, we get some factors out front, but we get the function back again. And with sines and cosines, that would not be the case. So this wave function is what we call an eigenstate in energy, and also it's an eigenstate for momentum. This would be representing a particle that has just one value of energy and just one value of momentum. Now this is quantum mechanics, so once we get into this a little further, we're going to find out in general particles don't have just one definite energy or one definite momentum, but this particular mathematical wave function does. All right, now if we're going to have wave functions, where are they going to come from? And they come from solving differential equations. So this is what's called a wave equation, what we're developing here. So we're going to create differential equations, and we're going to base the differential equations on energy and momentum formulas that we've worked from. Now, the most recent energy and momentum formula we worked from was in chapter 36 when we introduced special relativity. And back in chapter 36, special relativity, we found out that the fundamental energy momentum formula within relativity is E squared is equal to PC squared plus MC squared squared, where E is the total energy, P is the momentum, and M is the mass of the particle. So what we can do now is we can take what was E squared and replace it with the energy operator twice. So that's what I've written. I've said, okay, I'm going to take E squared and I'm going to take a wave function and I'm going to operate on that twice. I'm going to operate on it once, take a partial with respect to t, multiply by IH bar, take another partial with respect to t, multiply again by IH bar, and that's my wave function. Now for momentum squared, I'm going to factor out the c squared, and the momentum squared, if you remember, was minus h bar, partial with respect to x, and so I'm going to operate on this twice with the momentum operator, and then the factor of c is out front. Now for mc squared squared, mass is just a scalar property within special relativity. We're just going to be multiplying the wave function by that value. Now if we've done this right, when we take the energy and momentum operators and operate on these wave functions, we'll get that equation back again. So we'll get back to this equation. So again, it is circular, the argument, but what we're showing is we have a mathematical consistency, and it's making predictions about which functions can be wave functions and which functions will not be wave functions. So what I did was I followed through with these definitions, and the i's multiplied together give me a factor of -1. So I got -1 here and here. I got a couple of factors of h bar right there. I got a factor of c squared here that I've been bringing along with me. mc squared squared times the wave function. Now that turns out to be a wave equation, a partial differential equation that applies to particles traveling from point A to point B, following the rules for special relativity. So we could use this. We could use this for all sorts of particles. It turns out we don't in many cases. If we have a particle that has an enormous amount of energy, then it's moving really fast. We may use this equation, but in general we see that we use a different equation. But we do use this for photons. So this equation does get used for photons. Now, for photons, m is equal to 0 as far as we know. So that term drops off. And we can also eliminate h bar squared on both sides. So in the case of photons with no mass, this relativistic wave equation reduces down to second partial with respect to time is equal to c squared times the second partial with respect to x. Now that's been known from way before quantum mechanics. That is the Maxwell wave equation. that was developed during the mid to later 1800s as a way of expressing the propagation of light. So it turns out that a little piece of quantum mechanics was already understood when people had developed electric and magnetic field propagation, and Maxwell had derived this formula. That's actually a quantum mechanical formula. Okay, you may have seen that in Physics 4B. So here's an alternate wave function that we could use. Instead of using relativity, which you would be thinking that would be more accurate, it would be more inclusive, it would work in more cases, it would be more general, but it's more common to work in what's called the Schrödinger equation. Now, this is non-relativistic, but what it does allow us to do more easily is to introduce the idea of potential energies. So potential energies are a little easier to incorporate if we're not using relativity. And so what we're going to do is start with a statement of energy is K plus U, but you guys realize the big E here, that is not the total energy from relativity. This is a different total energy from classical physics, where I have a particle with some amount of kinetic energy, and I also have some potential energy. Now, this is going to be really handy to work from, because when we start looking at electrons inside atoms, or if we're looking at protons and neutrons in the nucleus, we need to be able to have both kinetic energy and potential energy contributions to the energies that we're calculating. Okay, so that becomes important, and we can use the Schrödinger equation to come up with those quantum states. So the K is the kinetic energy, the U is the potential energy. If I take the Schrödinger equation and I write it in operator form, there is an operator for energy, total energy, but there's not an operator for momentum. Okay? Now, there's not an operator for kinetic energy. We have a momentum, an operator instead for momentum. So let's see how we can take kinetic energy and convert it over into momentum, and that derivation is listed there. So that says that the kinetic energy, we need to replace that with 1 over 2m times p squared, which is the momentum operator, and then there is the potential energy term. So the E gets replaced with the energy operator, the momentum squared gets replaced with the momentum operator twice, and this is what's called the Schrödinger equation. So you may have seen this in some chemistry classes or talked about it. So we're going to actually be using this. So we're going to actually be working with the Schrödinger equation and solving for different wave functions that satisfy the conditions of the Schrödinger equation. As you can see, it's a partial differential equation, right? So the wave functions we're going to be using are going to be functions of x and t. Sometimes what we can do is, instead of solving for the energy also, or solving for the time dependence, what we can do is just say, we've already solved it, it's energy, it's E, and just plug that in. So in those cases, it's what's called the time independent formula. This is the time dependent formula, where the time dependence is still built in. We're going to see both cases. We're going to see cases where we want the time dependence to still be part of what we're looking at, and then other times when we don't need to look at the time dependence so closely. Well, here is that wave function again. So let's take a look at some more of its properties. Now, this wave function, we know what its momentum is because we can solve that by using the k value, the wave number. We know what the energy is of the particle because we can use the omega to give us the energy. Now, the next item that we need to look at is, where is this particle located? If this is a wave function, it's not going to be located at just one point. It's going to be spread out in space. Now, what happens when we try and calculate the probability of this, probabilities come from squaring the wave function. More specifically, it's what's called modulus square. So a modulus square means you take a function, multiply by its complex conjugate. Now the complex conjugate of e to the ikx is e to the minus ikx. A complex conjugate is the very same expression where everywhere there's an I, the I gets replaced with negative I. And so if I take the wave function and square it, I'm going to get two factors of A. I'm going to get an e to the ikx, but I'm also going to get an e to the minus ikx. And you know, if I take e to the ikx times e to the minus ikx, that's e to the 0. That's 1. And so exponentials have this very interesting property. When we use complex or imaginary arguments for the exponentials, the product of their complex conjugates is just equal to 1. And so what that tells us is that when I take the modulus squared for this generic wave function that we've been looking at, all of the x and t dependence goes away, and it's just a steady constant, a squared. Now that becomes a bit of a problem for us, because what that tells us is that this particle, this wave function that we've got, is describing a particle that is equally likely to be found anywhere in space, anywhere along the x direction. Well, that doesn't seem very useful. We want a mathematical function that describes a particle that is what we call localized, a particle that's in some region of space, because we can follow trajectories on some of these particles. So something that exists equally likely everywhere isn't necessarily the most useful particle to work from. Now when we look at the time dependence goes away. Now this is kind of interesting. This says that the particle exists at all time. And that just means it's a stable particle. And so something, or a stable quantum state. So a stable quantum state that has this e to the I omega t, actually that works pretty well. So as far as the time dependence, the e to the I omega t, we're going to be using that a lot. Any stable particle, any stable quantum state is going to pick up that factor. But the e to the minus ikx, we'll use it, but we'll use it less frequently. We'll see how we have to alter that. So anyway, this is an interesting wave function because it's representing something that has one particular momentum value, one particular energy, but it's located everywhere, and it's equally likely to be at all times. So it exists over all time. So this leads us to the idea of using not the wave function that we were looking at, but something called wave packets. Now it turns out that if we go back and look at that generic wave function that had a definite momentum and a definite energy, what would happen if I took a bunch of those functions? If I took a bunch of those wave functions, but they each had a slightly different energy and momentum. Well, that would mean that I no longer have a particle that just has one definite energy. It would have a range of possible energies and a range of possible momenta. But on the other hand, what happens when we do that is we are able to create localized particles. We're able to create what are called wave packets. Here's an example of a wave packet that we use frequently. It's a Gaussian function, or a normal function if you've seen this in statistics. And it's e to the minus x squared over something to show how much it's spread out. One way we could write the wave function would be a e to the minus ix over 4a squared. The probability distribution would come from squaring this. Now squaring this would turn it into e to the minus x squared over 2a squared. Now the a in here is known as the width of the distribution. So if you've seen this in statistics, or if you've just seen this in mathematics courses, this Gaussian function, there's a certain width that we define. Now, in physics terms, what that becomes is the range of possible locations where the particle could be found. So I've got a wave packet now. There's a limited range of where the particle could be found. It's not going to be found just anywhere at all. It's going to be found over some region. Now, in order to create a Gaussian function in terms of x, it turns out that that's correlated with a momentum function that also is a Gaussian. Gaussian functions have this property that the distribution in x and the distribution in momentum are what we call Fourier transforms of each other. Not sure if you've heard of Fourier transforms. You've probably heard of Fourier series in your math classes where you add sines and cosines together to create any shape function you want. That's what's going on here. What we're doing is we're taking not sines and cosines, but we're taking these complex exponentials. If I add together these complex exponentials in the right manner, I can create any function I want. Those complex exponentials form a basis set of functions. So by varying the momentum, I can create a particle that has a range of possible momentum, in this case described by a Gaussian function, and a range of possible locations. Now what we find is that the A in here is giving us the width of the x distribution, and the B in here is giving us the width of the wave number. Now the wave number is proportional to momentum, so we're working in terms of wave number right now. What we can show by taking Fourier transforms back and forth is that A times B is 1. So these two distributions are Fourier transforms of each other. They're related to each other. And I can substitute in for A and B. That's delta x and delta k. That's going to be equal to 1. And since momentum is h bar times k, I can multiply through by h bar and write down the range of possible locations times the range of possible momentum, how broad that range is, multiplied together is equal to h bar. And that's referred to as the Heisenberg uncertainty principle. Now, just to show you what these Fourier transforms look like, this is a more general representation of any two functions related through the Fourier transform. If you guys are if you're majoring in physics, you're going to see this. If you're majoring in kind of anything electrical engineering, for example, if you're looking at signal processing, you're going to be looking at Fourier transforms all the time. When you send a signal through a circuit, you can represent it as a pulse in terms of the current that's going through. You can also represent it as a collection of different wavelengths of that particular function. So that's what Fourier transforms allow us to do. So that's the idea, is that there are these pairs of functions that are related through Fourier transforms. So there's what's called the Heisenberg uncertainty principle, and it's the same thing that we had come up with here. This is h bar. It says that when we combine the width in the x distribution, what is the amount, the size of that range of values, and then the range of possible, how wide is the range of possible momentum values in the corresponding direction, in the x direction. It's h bar. And so this is called the Heisenberg uncertainty principle, and it tells us that position and momentum, here it says can't be simultaneously measured. What it says is that the wave functions that we work with are not going to have one definite location or one definite momentum. They're going to have ranges of possible locations as to where these are found. Now, in case my drawings weren't really good, I plotted this. This is a Gaussian function, and I scaled it to be height 1 at the center. But you can see the different widths on this, and that's what I wanted to show. If we were to take a particle and confine it into a smaller and smaller region, how would we do that? And what this is telling us is if I try to get better and better information about where the particle is located, I'm going to have a wider and wider range of possible momentum for that particle. So these are correlated functions. If, on the other hand, I try to go back and get a particle defined by a very definite momentum, in order to have a particle with just a very definite momentum, I'm going to have a broad range of possible locations as to where the particle can be found. So you can't do both at the same time. It's just built into the properties of the wave functions and the operators. The way that we're representing these as wave functions means that there's always going to be these products of uncertainty, or as I like to think of it, as possibility. The Heisenberg possibility principle, because it's possible to be in more than one location, and it's possible to have more than one momentum. Now there's a related Heisenberg possibility formula, and that has to do with range of possible energies, how uncertain is the energy, and the amount of time over which that quantum state exists. So it says that if quantum states only last for a short amount of time, there's a range of possible energies. Particles that are stable, or quantum states that tend to be very stable, will have a very definite energy to them. But particles that rapidly decay, particles that do not have a long lifetime, for example, could have a wide range of possible energies or possible masses. So mass turns out not to be a well-defined property if the particle has a short lifetime. All right, let's try a couple of these problems. Now, I should say this up front too, this Heisenberg stuff is useful. It's probably not as much of an emphasis for us as the later part of the chapter, but we're going to go ahead and work through a fair number of these Heisenberg possibility principle problems. So for example, let's say we have an electron. It's moving, now here it claims it's moving in a straight line. Let's just say that's its general direction, going from point A to point B, and the speed is like 1,000,000 meters per second, and it's being measured, the speed has been measured to a precision of 0.10. Now, what they're really saying there is that we want to represent this particle with a wave function that represents something traveling this fast, but there's a range of possible velocities. Now, one thing we should point out here too, with these particles, when we're saying, well, there's a range of possible velocities or a range of possible momentum, that means that even though the particle may be localized at one instant, because it's got a range of possible momentum, as time goes on, that wave function spreads out. So the wave function tends to spread out. We tend to become less and less certain about where the particle will be located or where it might interact. So what they're asking us here is, okay, here's a picture of our electron, and it's got a mass m. Now I started to draw a little particle here, but then I drew something a little fuzzier. So I'm going to say, okay, the electron is kind of spread out. It's got some distance from front to back of where the electron could possibly be. Here's the velocity it's traveling at. I'm going to go with our standard wave function that we've been using for free particles. So the k is momentum over h bar. The omega here is e over h bar. So energy and momentum's built in. And let's find out. This is the Heisenberg uncertainty principle right here that we've got. So let's try, I guess it's this side first. So let's find out how much momentum this electron has. Now they told us it's traveling at 1.10, 10 to the 6 meters per second. here's the mass of the electron. So I took momentum as m times v. And m times v worked out to be, I think they gave us numbers that would do this, 1.00 10 to the minus 24 newtons times seconds. Those are just standard momentum units. Now it says that the velocity has been measured to 1 part in 1,000. So it's accurate to 3 significant figures. That says that the uncertainty in the momentum will also be accurate to 1 part in 1,000. So it's saying that the momentum for this electron is 1 times 10 to the minus 24 plus or minus 1 times 10 to the minus 27. All right. So that's that variation of 1 part in 1,000. Now if I convert that into PC for kind of relativity purposes, since we're working with electrons, we tend not to use Newton seconds. We tend to work in terms of PC and EV. So what this worked out to be was this electron has a momentum of 1,875 eV. And the plus or minus then would be 1 part in 1,000. That would be plus or minus 1.875, or plus or minus about 2. So the momentum, the average momentum for this particle, 1875, but its momentum could be as low as 1873, easily be as low as 1873 or as high as 1877. So the uncertainty principle is telling us it's not just a mismeasurement, it's not a limitation in our measurements, it's representing particles with wave functions. In order to represent particles with wave functions and have them be somewhat localized, we're going to have to allow for a range of possible momentum values. Now, what they said in the problem also is they go, okay, let's write down, well, we did this part, write down how much uncertainty or how much delta P there is in the particle. What we could do now is we could take delta X, and delta X could be set equal to h bar over delta P. And then what I did was I added factors of C top and bottom, and then I factored out this should become hc over 2 pi. So there's my 1 over 2 pi, there's my hc, 1240, our friend from chapter 2037 and before even. And what I ended up with was, with this much uncertainty or this much range of variability in the momentum, we're going to have this much, at minimum, we'll have this much uncertainty as to where the particle is located. So this particle is not knowable. Its location is spread out. It doesn't exist at just one location. It exists over a range of at least 105 nanometers. Okay, now that's small in terms of stuff we were doing in physics 4A and most of the stuff in 4B, but now we're going to be looking at atoms, and that's pretty big when you start looking at atoms and molecules. That's a pretty good size. Now, there are also relationships between delta Y and delta momentum Y, delta Z and delta momentum Z. We're going to find out that there are possible momentums, X, Y, and Z, and possible locations. In fact, we just found that out. We're not going to be looking at it that much more in depth. So let's go back and see, for this wave function, how would we build that in to the properties of the wave function that we've got. So we could start with a wave function that has a momentum of 1875. The k value that would go along with that, so I went through and calculated the k value, that worked out to have a phase variation of 9.5 radians per nanometer, or a wavelength of 0.661 nanometers. As far as the frequency we can get by taking energy over h bar. Now, here we do need to go back and use a little bit of relativity, because for the particle, most of its energy is in its mass. if it's a slow, relatively slow moving particle, the kinetic energy will be small compared with mc squared. So we do need to include mc squared. Now I just used the relativity formula full blown here, but you can see that basically what we have is an energy that it's essentially the energy of due to the mass of the electron. So I put that in to calculate the frequency, and that came out as 7.77 10 to the 20th radians per second. So, and a period of 10 to the minus 21 seconds. So we're trying to relate those phase values of wavelength and period along with the momentum of this electron. All right, now what always happens in quantum mechanics is you start wondering, well, this works so well for small particles, electrons and protons and such. Does it work for big objects? And so here is our uncertainty of a baseball problem, and it's saying what's the uncertainty in the position imposed by the uncertainty principle on a baseball thrown at 42 meters per second, 150 gram baseball. Now that's a pretty good speed, right? 93 miles per hour, or 40 meters per second for the baseball. It's like a major league pitcher here. So let's take a look and see what we've got. Here's the baseball, here's the speed, here's m. I'm basically doing the same thing we did with the electron just to see what's going to happen this time. Now in this case I wrote down the mass, I wrote down the speed. Now that's a pretty wide uncertainty in the speed. I was surprised to read in the information that was given. It told us that the baseball actually has a range of possible velocities between 41 and 43. Now, we don't tend to think of macroscopic particles as having that much uncertainty. If we got out some really precision measuring devices, I think we could measure it more accurately than this. But they're throwing that in there. So they're saying, what would happen if we had, now I calculated the momentum. The momentum came in at 6.30 Newton seconds, and the uncertainty, or the range in momentum, the range of possible momentum, came out to 0.15 newtons times seconds. So I plugged it in. I plugged it into the Heisenberg uncertainty formula, and plugged in or solved for delta x, and it says that the uncertainty in the baseball's position is 10 to the minus 34 meters. Okay. Now that's really, really extraordinarily tiny. I don't know if that's really very meaningful or not. So it's always to me, it's always kind of up in the air about can we really take these principles in quantum mechanics and apply them to these really big, everyday complex objects that have a lot of stuff going on in them. Here's one last example that we can take a look at and squeeze this in before break. Break is coming up here. There is a particle in particle physics. There's a particle called the J psi. And the J psi meson, discovered in 1974, about the time when I was back in high school, was measured to have an average mass of 3,100 MeV per c squared. Note the use of energy units. So we're carrying over the energy units that we used from chapter 36. And an intrinsic width of 63,000 eV. Now, what we mean by this is that the J psi has such a short lifetime. Let's move on here. The J psi meson has such a short lifetime, it does not have a definite mass. There's a range of possible masses at which the J psi can be generated in particle accelerators. In our laboratories, we can generate these particles. We know how. It's not so difficult anymore. We've been knowing how to do this for 20 years, almost 50 years now. But here's what you actually see in these experiments. let's say that, well, in 1974, where this particle, one of the locations where this was discovered was at the Stanford Linear Accelerator Center, and they had just recently put together an anti-electron storage ring, which allowed them to run reactions with electrons and anti-electrons at a pretty good rate. And what they could do is slowly increase the energy of those electrons and anti-electrons, and they could just look for new particles. Now, the way a new particle would show up is as you increase the rate, you would go, no, no reactions, nothing's happening here. And then all of a sudden you would see a lot of decay particles show up in your detector. And so that would indicate that you've stumbled upon a new particle and you've created that new particle. So this was the J psi, and at the Stanford Linear Accelerator here just on the peninsula, researchers, once they had discovered it, it took them, when they first turned the machine on, they knew that they were going to be able to very carefully scan for any new particles in this energy range. And so it was really just a matter of days until they made the discovery. And then they could map it out very carefully. And so as they went to higher and higher energies, you would start to see a few of these particles generated. And then right at 3100, or whatever the mass is, you would see more. It would peak and then it would drop off. So there was a range over which you were generating these particles, and that delta E range was 63,000. Now, what we can do is we can take that range of energies and plug that into the Heisenberg possibility formula for time and energy. And what we end up with then is that we're predicting this particle has a lifetime, this particle that we observed through its decay products has a lifetime of 10 to the minus 20 seconds. Now, none of our detectors can pick something up that decays that rapidly. They can't pick it up directly. So what they're doing here is they're looking at all the particles when the J psi decays, it turns into some number of particles, and researchers can do what's called reconstruct the original particle that they decayed from using energy and momentum conservation, and they use that to determine what the they can use that to determine what the original mass was. So they can look at the mass and see if it verifies with the energies that the beams of electrons and anti-electrons were at. Now, in solving this, I used h bar, but I used it in EV seconds. So I wrote these all down, I thought, we're getting into where we're using h a lot, we're using h bar a lot. A lot of times we want to have these in EV. So these are good things to have in your notes. You can bring these in on your formula sheets for the exams, which we have coming up in the not too distant future, right? Let's see, what is it, next week it's coming up. So the midterm is coming up. So these are good to have. If you have all of these versions, then you don't have to stop and do conversions during the midterm. You just already have them on your sheet ready to go. Okay, so this is probably a good place to stop. So I'm going to stop there. Let's take a break and then we'll come back and we will pick up with more chapter 38.